So this slide is supposed to show refraction in one dimension, and refraction in one dimension is really boring. All that happens is the wavelength gets shorter, and it gets shorter by the ratio of the indices of refraction. So if this is essentially a index of refraction of 1, and this is 1.33, you can take the wavelength and divide by 1.33, right? If this is 1.33 and then it's like diamond, you're swimming with your diamond ring on, right? You know, right? If this is 1.33 and this is 2.42, you would use that ratio to make the wavelength smaller. Yeah, does that make sense? So I guess what would you do? You'd multiply by 1.33, divide by 2.42, because that would make it smaller, yeah? Yeah? Okay. So that's the way that works. But if it hits at an angle, then things get a little more exciting. And this is, of course, nobody thinks that refraction straight on is refraction, but it is. Okay. But if it hits at an angle, then this is a lot more fun. Let's see if we, oops, what did I just do? Okay. If it hits at an angle, then of course what it does is, well, I don't know if it's an of course, but it bends. Yeah. And so here we've got a laser coming in, and it's striking this water. Not if you can see the beam of light here. Can you see it? I know. Yeah, let's turn it off. Maybe we can see it if we turn the light off. Yeah. Can we see the beam of light here? Yeah. Why can't we see it? Because it's like, because there's nothing there to scatter the light. So it's a Star Wars, all that thing where you can see the laser lights. They just did that because this is kind of boring, right? Okay. So what I'm going to do here is I'm going to put some stuff in the air. Okay. Yeah, there's got to be something here to scatter. If the air was dusty, then you could see it, right? So what I'm going to do is I'm going to make the air dusty. I've got here, this is some Lycopodium powder. Do you guys know what Lycopodium powder is?
Lycopodium?
No? It is.
They come from a plant, I bet.
It's definitely, you know. It is, Lycopodium powder is dried anthrax spores. Can you see the beam now? Do you see it bending?
Yeah.
I don't like it.
Yeah, this is, the air is fast, the water is slow, and when it hits the water, it bends into the water. Yeah, that kind of makes sense to me inherently, right? That if you hit see the reflection too, it's also reflecting off. So it's two REF words, right? It's reflecting off the surface and hitting up there. Yeah. Yeah, it's like moving, right? Okay. And then it's also refracting into the water. And then, of course, you know, when it hits this edge, it refracts. Yeah, that's a word that's a combination of reflect, and refract. Yeah. So there it is. But we're just going to look at that first bend there. Well, it will right at that surface, right? And I'll show you why it does, why it has to. But let's turn the lights on first, because it's always easier to see when the lights are on. Let's give the laser a big round of applause. Pour le laser. All right. I better put this down here because I know I'm going to probably just gesticulate and knock it over. No, Lycopodium powder is actually just like dried pine pollen. It's kind of fun. I was just joking about that. Anthrax is a white powder. I don't even know. I don't know. Okay, so draw a very careful picture. This is also on the first page of the test, which you might choose to cross off, but you might not, so write it down. And I will show you why the light bends, why it has to bend, and how you calculate how much it bends. All of that with one drawing. Okay, so this is going to be like one of the best drawings ever made in the history of drawing refraction problems on the whiteboard in this class. Voilà. Regardez ça. This is my, I've patented this. No, I haven't yet. Okay, this is my little guide. This is the wavelength in the air. Okay, this is going to be the wavelength in the substance. So what's my index of refraction, roughly? not a half. Nothing can be less than 1, right? That means it's going faster than the speed of light. It's exactly twice as slow, right? Yeah, yeah. Twice as fast in the air, half as fast, or something like that, right? Yeah, I don't know, right? So this is the wavelength in the air. It's going faster, so it's a longer wavelength. In the substance, it's the index of refraction apparently is 2. Okay, so let's draw the surface of some medium. Okay, draw it very carefully, and we'll just make the slower medium be on the bottom, so it's like going into water. Okay, so this is slow. Slow, by the way, is small wavelength. And then this is fast. This will be big wavelength. Yeah? And then let's make the beam of light come in at some auspicious angle. Comme ça. Here's the beam of light. Now, in physics, we don't talk about this as being the angle of incidence. We, talk about this. We draw a line normal to the surface, normal being that, meaning right angles to, right? And then this is our angle of incidence, right? And then there's going to be an angle of refraction, but I'm not going to draw that one just yet because I'm going to let the wavelengths show me, okay? So what this diagram is supposed to be showing you is that these are like the crests of the wave. These are like ocean waves coming in, only it's a light wave, and those might be the peak of the electric field or something like that. This distance here is the wavelength. This beam of light is traveling this way, and we see those crests coming in, and we turn this way because the wavelength shortens. It has to bend because it shortens. So let me show you how to draw that drawing. I'm going to start this guy here, right there, and I'm going to put one of the wavelengths right there. Yeah. And then I'm going to draw this guy here. And I'm going to draw another wave out here. Let's draw another one here just for good measure. And I do this red because this is our laser beam coming in here. We're greatly magnified, aren't we? Yes? Yeah. Okay. Now we've got a little thing going on here because basically, I got to draw the next guy here too. Here's the other wave as it disappears under the surface, right? Okay. Now the wave's got to get shorter in the substance, doesn't it? But here's one of the rules, and this is the Huygens wave principle, is that these crests have to be continuous underneath the surface. So how do I do that? Does this work? Does the crest under the surface match up with that one? Does it? That doesn't work so well, does it? But what if I bend the light? Can it then match up? Huh? Et voila. Yeah? Now it matches up. Here's the crest below the wavelength has shortened. Right, we're now going in this direction. Isn't that beautiful? It has to bend because it has to get shorter in the substance, yeah? Yeah? That's beautiful. Let's draw this guy here. Okay, and then this should also work like this. I should be able to do a thing like that. It's almost working, right? I'm not very good at this. There we go. Right? And we'll just keep going in this direction. So in shortening the wavelengths, you have to bend the beam of light. And of course, now we have a new angle that the wave is going. It's now going this direction. We need the black. Can't draw it any other way, can you? There's no way to draw these wave crests as continuous, right? Without and short.